So today we are going to study about JVM architecture. Imagine this. You deploy a new version of your payment service. First 3 minutes after deployment, P99 latency jumps from 20 milliseconds to 400 milliseconds. The manager is panicking, users are complaining, then suddenly it fixes itself. Nobody on your team knows why. I'm going to show you exactly why this happens, and it all comes down to understanding what the JVM is actually doing underneath your Spring Boot application. Let's go. Why does the JVM exist? Let's go back in 1991 when the Sun Macrosystem is building a software for consumer electronics, set-top boxes, remote controls, embedded devices, and much more. The brutal problem. Every device has a different CPU architecture. Every device has a different CPU architecture. Code compiled for Motorola won't run on Intel. Code compiled for Intel won't run on Spark. You had to rewrite and recompile your software for every single target platform. This was the write once, compile everywhere nightmare. Then James Gosling's team at Sun had a radical idea. What if instead of compiling to machine code, you compile to an intermediate instruction set? In an imaginary set that no real CPU understands, but then you also ship a small program called a virtual machine to every device. That virtual machine understands the intermediate instructions and translates them to the real machine code of whatever device it's on. That intermediate instruction set is called bytecode, and that virtual machine is the JVM or Java Virtual Machine, which solves all the problem of write once, run anywhere. This single design decision compiled to bytecode, not machine code, created a cascade of consequences: garbage collection, JIT compilation, save points, the memory model. Everything will cover in this series flow from this single origin point. So this is the actual flow. So .java file goes to Java compiler, which then goes to class bytecode converter, which then goes to JVM, and which then goes to CPU for instruction processing. Section 2, the four major subsystems. Now let's open up the JVM and see what's actually inside. JVM has four major subsystems. First, the ClassLoader subsystem. This is the gatekeeper. It finds a .class file and loads them into memory. Second is the runtime data areas. This is the memory, heap, stack, metaspace, where everything lives while your program runs. Third is the execution engine. This is the brain, the interpreter, JIT Compiler, GC. This is what actually runs your code. And fourth is the native method interface or JNI. This is the bridge to the operating system. When Java needs to do something JVM can't do, like talk to hardware, it goes through here. Let's dive into section 3, the class loader or the delegation model. When you write new loan service in your Spring Boot application, before that object can exist, JVM must first find and load the loan service class. That's the class loader's job. There are basically three built-in class loaders: Bootstrap, extension or platform class loader, and the application class loader. Bootstrap class loader is at the top, which is written in C++ and not in Java. It loads the core Java library, string, object, system, thread, everything in java.lang. Next is extension or platform class loader. This loads optional Java extensions. And the third or the last class loader is application class loader, which is what loads your code, your loan service, your Spring Beans, and your entire application. They don't work independently, they work on a delegation model. When the application class loader is asked to load a class, it does not try to load it immediately. It delegates up to the extension class loader. Extension class loader then delegates up to the bootstrap. Bootstrap class loader, which tries first. If it can't find it, control comes back down to extension class loader. If it can't find it, application class loader finally tries. Why is this design? Because it prevents you from accidentally or maliciously overriding core Java classes. You can't ship a fake Java length string and have it load because Bootstrap class loader always gets first priority. Loading a class has three sub phases basically, which is first loading, which finds class bytes and read them. Second is linking. Linking has independent three steps inside, which is first verification. Verification checks if this is the valid bytecode. Second is preparation, which allocates memory for static fields set to default. And the third is resolution. This replaces symbolic names with real memory pointers. And then the third is initialization. Run static blocks, assign real values to static fields. So these are the delegation models. First, second, and third steps. Section 4 or the runtime data areas, where everything lives. Once the class is loaded, JVM needs memory to run it. 5 runtime data areas we have. The heap, the biggest box shared across all threads. Every object you create with new object lives here. This is what the garbage collector manages. Hidden spaces, survivor spaces, old gen, all inside the heap. Second is Metaspace. This lives outside the heap in native OS memory, stores class metadata, structure of every loaded class, field names, method bytecode, access modifier, constant pool. Before Java 8, this was called permgen and had a fixed size, causing the famous permgen out of memory issue. Metaspace autogrows, probably mostly gone. The next comes as Java stack. This has all the thread stacks per thread. Each thread gets its own stack. Every method call pushes a stack frame. Every method returns pops and that frames. Each frame contains local variable, operand stack, constant references. This is why infinite recursion causes stack overflow exception. The stack is finite. Each recursive call pushes a new frame until the stack is completely exhausted. In this you can see we have already three entries here. If we try to create another entry here, this goes beyond the stack space and which may lead to stack overflow exception. Next comes the PC register or the program counter. Program counter also per thread. It holds the address of current bytecode instruction being executed. When the OS pauses a thread, context switch, it saves the PC register. And when the thread resumes, the JVM reads PC and knows exactly where to continue. And last is native stack or the JNI. It is for JNI calls. When your Java code calls a C++ native method, execution happens here inside of the JVM stack. Section 5 Execution Engine, the JIT magic. This is the most important subsystem to understand. When your Spring Boot service starts, how does the JVM actually run your bytecode? It doesn't compile everything upfront, that would take too long. Here is what actually happens. The tier 0 or the interpreter. JVM starts by interpreting bytecode, one instruction at a time. Fetch the bytecode instructions, decode it, execute it, and fetch the next. Slow, but instant startup, no compilation time. First request is served immediately. But the JVM is also counting. Every method has an invocation counter and every loop has a back edge counter. When a method gets called roughly 2000 times, JVM says the method is getting hot. Now it's time to invest. Here comes the tier 1 to 3 or the C1 compiler. It is the client compiler, has light optimization and compiles very fast. It compiles that hot method to native machine code quickly. The method now runs as actual CPU instruction and no more interpreting required. JVM keeps counting. When same method hits roughly 10,000 to 15,000 invocation, Here comes tier 4 or the C2 compiler. C2 is the server compiler, slow to compile, but output is aggressive. C2 does three things: method inlining, escape analysis, and loop unrolling. If your customer service calls credit score calculator.calculate method and that method is small, then C2 copies the body of calculate directly into customer service. No method call overhead at all, which means method inlining copies the body of a callee method directly into the body of a caller method to eliminate CPU overhead of a standard method invokes instruction. Second is escape analysis. If an object is created inside a method and never leaves that method, C2 allocates it on the stack instead of heap, 0 GC pressure and 0 GC pause impact. The third is loop unrolling. If you have a loop that runs 10 times, C2 may unroll it into 10 sequential operations, eliminates branch prediction misses. The result: same method that started as interpreted bytecode can end up running 50 to 100 times faster at already steady state. Let's look at the latency time graph. Here you see as and when time increases, latency decreases because C1 and C2 comes into the picture and do optimizations which further reduces latency. This whole system is called tiered compilation, which is default since Java 7. Now if you remember the deployment problem from the beginning, you deploy a new jar, fresh JVM, first 500 requests, all interpreted, slow, and then next 2000 requests comes, C1 compiled faster. Next 10,000 requests came, C2 compiled. Now it works at full speed. That latency spike you see after every deployment is the JVM warming up. So what is the architectural fix? Blue-green deployment. Spin up the new instance, send it synthetic warm-up traffic, not real user traffic. Wait for JIT to warm up, then shift production traffic over. No latency spike, clean deployment. So here's the complete picture of JVM model. Your Spring Boot service starts, OS creates a process, JVM initializes. ClassLoader loads bootstrap classes, which is string, object, thread, then loads Spring classes, then loads your classes based on delegation model, always up first, then down. Second comes the runtime data areas activate. Heap created, Metaspace is allocated in native memory, each thread gets its own stack and PC registers. Then comes execution engine, which begins by method interpretation. JVM profiles, C1 fires, C2 fires, GC watches the heap, minor GC need and spaces occur, major GC in old generation appears. Native interfaces bridges to the OS when needed. That's it. That's the whole machine. Every topic in the series, transactions, caching, Kafka, Kubernetes sits on top of exactly what we just drew. So here comes our interview rapid fire. What is the difference between JVM, JRE and JDK? JDK contains JRE plus the compiler and DevTools. JRE contains JVM plus the standard library. JVM is the execution engine, which has ClassLoader, data areas and execution engine. And JDK is a superset of JRE, which is a superset of JVM. From Java 9, JRE is a separate download which is deprecated for now. Second, what happens when you get a Stack Overflow exception? JVM stack for that thread is exhausted. Each method call push to a stack frame, usually infinite recursion, base case missing. Stack has configurable size via -access flag, which we will study in our garbage collection series. What is Metaspace and how is it different from old PermGen? Metaspace stores class metadata. PermGen was on the heap with a fixed size, which causes out-of-memory error when too many classes loaded. Metaspace is in native OS memory, auto grows by default and has no fixed size. You can still cap it up with access max metaspace size. What is tired compilation? JVM starts method in the interpreter, profiles invocation counts. C1 count compiles at roughly 2000 invocations, which is fast compile and light optimizations. C2 compiles at roughly 10 to 15,000, which is aggressive output. In learning, escape analysis happens at this stage. Best of both, fast startup, peak performance at steady state. Here comes the staff level question. A service spikes in latency after every deployment. Root cause and fix? Cold JVM, JIT not warmed up. Fix? blue-green deployment with warm-up or gravel AOT native image. Yeah. Trade-off: native images loses runtime adaptive optimizations, which C2 can't profile and inline based on actual traffic patterns. Here's the JVM architecture revision. Why Java JVM exists. It gives feature of write once, run anywhere. Compile to bytecode, not machine code. JVM translates bytecode to native instruction at runtime, which further converts to machine code. Your subsystems. Four subsystems. ClassLoader, runtime data areas, execution engine, and native interface or the GNI. ClassLoader delegation. Bootstrap occurs in C++ language, not in Java. Always delegate up first, then down, and it prevents overriding core classes. Third comes runtime data areas, which is Heap, Metaspace, JVM stack, PC registry, and native stack. Where JVM stack, PC register, and native stack are per thread allocated, and metastases are native on the OS. Heap is shared and GC managed. Execution engine, which is also has tired compilation, which has tier 0 or the interpreter. Tier 1 to 3 is the C1 compiler, and tier 4 is the C2 compiler, which has inlining, escape analysis, and loop unrolling. Cold start problem. Fresh JVM uncompiled, hence slow. Fix blue-green with warm-up or gravel native image. So JDK is superset of JRE, JRE is superset of JVM. JRE is deprecated as separate download from Java 9.